Okay, thank you for inviting me. Now, come here. Today's lecture is supposed to be pedagogical. So,
yes.
So I'm going to cover a lot of things that are not my own work, but I'll also show you some work. And the topic that I was given by Professor Kawashima was to talk about the connection between quantum Monte Carlo and field theory. Okay, so I'll tell you about a little bit about some background, but I have a website where I put up my notes for this lecture, and there's some more details over here, so I won't be able to cover I probably won't be able to cover all the details, but I'll just give you the gist of the story, and then if you're interested in more details, you can read about on this web page. And I put up the notes that I have, but I'm going to update it and make it a little better. Okay, so let me begin with a quick review.
Ribhu?
Yeah.
What is the character next to EDU slash?
Oh, sorry. This
Is it tilde?
Yeah, tilde.
Oh, tilde. Okay.
Tilde and then RKK. So that's just my university homepage, and you can follow the links to this. So even if you just Google search my name and you go to my homepage, I think you'll find these notes. Okay, so I'll begin with a quick review, and I assume that many of you are familiar with this ideas. And then I'll get to the topic. Okay, so the whole technology of field theory and renormalization group is very powerful, of course, in understanding classical statistical mechanics. And this is a very well-known topic. Both of these are classic textbooks. This one is really my favorite textbook, where you can learn about the details of how field theory can be used to connect to the lattice models of classical statistical mechanics. So today we'll want to talk about quantum statistical mechanics, but I'll just quickly tell you about classical statistical physics. So the simplest model you can imagine is, and I don't think I have to introduce this very much over here, is the Ising model. So there's an energy to make spins parallel. Spins can be up or down. So at low temperatures, all the spins want to be parallel. At high temperatures, because of entropic fluctuations, the system is disordered. And as you know, there's a phase transition between these two. And so if you study this model, so the partition function is defined as the sum over all configurations exponent minus e. So I've set the temperature to 1, and then this parameter j is my tuning parameter. And so the phase diagram of this model is very well known. In all dimensions greater than 1, which is 2, 3, 4, etc. There's a critical value at which you have a transition between an ordered phase and a disordered phase. Okay, so, this phase transition is close to the phase transition. This area very close to the phase transition is where the idea of a field theory becomes very useful. In the language of a field theory, this phase transition is described by renormalization group fixed point. Okay, so you imagine you're doing some renormalization group transformation, and there's a fixed point. And now we know that, for example, in 2 dimensions and in 3 dimensions, there are 2 relevant operators at this fixed point. Okay, so these are, so actually, let me just say it like this. So there are 2 relevant operators. Okay, what I want to emphasize is the connection between the lattice model and the field theory. Okay, so I mean, there's a lot of background that goes into understanding all of this, but and I'm assuming you're either familiar with it or you'll read about it later. But today I just want to emphasize the incredible power that this connection has, where you begin with a lattice model and then you study some property of the field theory. So there are two relevant directions, and they have a renormalization group eigenvalues, which are conventionally written as YH and YT. So in the Ising model, you can show that the operators that correspond to, if you just take the Ising model without a magnetic field, the operators that correspond to this relevant direction are forbidden by a symmetry. And so the only symmetry allowed relevant perturbation is YT. And so because there's only one relevant perturbation in the Ising model, you can actually reach the critical point in the lattice model by tuning one parameter. Okay, so this is a very interesting and important idea, that you can think about parameters in the lattice model, and you can think about relevant and irrelevant directions in the field theory. And there's a way of connecting all these things. And so the renormalization group flow, if you imagine that you have some irrelevant operator here, and you have the relevant operator over here, you can linearize the flow close to the critical point, and it looks like this. Okay, so the lattice model is believed to have all operators in it, all relevant and irrelevant operators. We don't worry about the irrelevant operators because typically they flow to zero. We only have to worry about the relevant operator. So there are infinitely many directions which are irrelevant, and this is just some cut that we're drawing over here. And so if you think about the Ising model as it's being tuned, it takes some trajectory in this parameter space, and so all these points over here will flow off in this direction, which may be the ordered phase, and all the ones on this side will flow the disordered phase, and then right this point here, which corresponds to critical temperature, actually flows into critical point. Okay, so this is a very interesting thing, and it's interesting for a number of reasons, some of which are going to be important for my talk, is that because many operators are irrelevant, it turns out that the critical point can have much higher symmetry than the lattice model. Okay, so this is a very remarkable and amazing phenomenon, that the lattice model only has a set of symmetries. So it has all the lattice symmetries and it has the inversion of spins. That's the only symmetry in the model. It turns out that at the critical point, if you look at correlation functions of the variables, they have a lot more symmetry than just those symmetries. And that has to do with the fact that infinitely many operators are irrelevant. Okay, so this is a very important idea, which is the idea of emergent symmetry. Okay, so the idea is that in a field theory, because so many operators are irrelevant, if you look at, so you know, the lattice model has a phase diagram which is like this, and you may characterize the phases and the physics close to the phase transition by certain correlation functions. So you may measure, for instance, 2-point correlation functions, and you can measure 2-point correlation. So 2-point correlation function just means that you have an operator and another operator and they're very far away. But you can measure more complicated objects, for instance, 2-point correlation functions of composite operators. You can measure 3-point correlation function, 4-point correlation functions, all these things. And the amazing thing is that if you look for correlation functions at very long distances, they are described by a field theory. And you know, one of the most celebrated results in this field is the emergence of conformal invariance. Okay, so it turns out that the critical point, the correlation function of the critical point, have such a high symmetry that in 2 dimensions, this symmetry is enough to actually constrain the kinds of critical phenomena you can have. Okay, so this is a very powerful result. And it again relies fundamentally on the fact that many operators are actually irrelevant. So your field theory has all the symmetries that are present in the lattice model, but it has many more symmetries. Okay, so this will be a very important topic, and we'll come back to this idea of emergence of a symmetry later in the talk. Okay, so I mean, sometimes you know, models have hidden symmetries. For example, like we learned the hydrogen atom, you know, it has a hidden symmetry which makes the atomics level for a given value of n, all the L values. But that's actually a hidden explicit symmetry that's there in the model. It's just not apparent when you write it down. This is something much more subtle because the symmetry is not present at all in the model. In fact, as we well know, at very long distances at the critical point, there's full rotational symmetry in space. And you know that the lattice model cannot have fundamentally a rotational symmetry in space, but this is something that emerges at the critical point.
Ribhu.
Yeah.
But I mean, at least that symmetry you also have in the high temperature phase, right?
Yes.
But are there some, I mean, these conformal symmetries, they only exist at the critical point, or are they also somehow there in some form in the high temperature phase?
I mean, in the high temperature phase, everything is so trivial that
Yeah.
I mean, I think you could say it probably has conformal symmetry, but it's not, it doesn't, it's very, I mean, all the correlation functions technically decay immediately.
But and also in the ordered phase, I mean, in some sense, many of these symmetries exist everywhere, right?
Yeah. But I would say the representation of them at the critical point is much more non-trivial. It's
I
complicated.
mean, of course, they have the power law decay, which they don't have in the other phases.
Yeah, so apparently this conformal invariance can restrict the kind of power law decays you
Yeah.
can have at the critical, which is amazing, because you wouldn't think that, right? I mean, so you can, using the power of conformal invariance, you can restrict what kind of power law decays you can have. Okay, so this is the basic setup, and so the question now is how can you apply this technology to a quantum model? Okay, so this is a classical StatMech model because these spins are just classical variables that commute with each other. So now we want to define spins which don't commute with each other, like the familiar spins that we study, but we can study more complicated spins than the simple SU2 spins we study, but in general they'll be described by matrices, and the Hilbert space is described by a tensor product of the single site Hilbert spaces. And so we can define these quantum problems, and the question is, how can you use this technology that's very well developed in classical StatMech to solve these problems, or to shed some light? Okay, so just to give you an example, and so this will be most of what I'll talk about today and then also tomorrow when I describe my own research. Is that imagine that you have a Hamiltonian. So I'll just give you one example. We'll study many, many examples. The most famous example maybe is the transverse field Ising model. In fact, I'll just study it in one dimension, so transverse field Ising chain. Okay, so this is an example of a spin model. So basically you imagine that you have a lattice, a quantum spin Hamiltonian, and on every side you define some local Hilbert space. So the simplest Hilbert space you can have is just two sites, which is, we call that the spin half. And then all the Hermitian operators that can act on this Hilbert space are the identity sigma x, sigma y, sigma z, like we know. And then you can construct operators which are tensor products so you can have spin. So basically the fundamental assumption is that the Hilbert space of the many body system is a tensor product of the one body Hilbert space. So the operators also, you can take tensor products of them. And so the question now is, we want to study the ground state wave function of this Hamiltonian. Okay, so in fact we're not necessarily interested in this particular Hamiltonian, I just wrote it down as an example. But in particular we're interested in the ground state wave function. Okay, so it's very different from classical statistical mechanics, because there you're studying partition function, a thermal partition function. Here we're studying a ground state wave function. And you can change some parameters in your Hamiltonian and ask how this ground state wave function changes. Right? So when we learn quantum mechanics, the way we calculate the ground state wave function is we diagonalize this Hamiltonian and we look at the eigenvalue of the lowest energy. And then we study how that eigenvalue varies as you change a parameter. Okay, so, again, the ground state can be in different phases, just like you have in classical statistical mechanics. And so then it's natural to wonder whether these methods can be used over here. And a priori it looks like they cannot be used, right? Because there seems like no relation. Here you're diagonalizing a many-body Hamiltonian, and there you're solving a statistical mechanics problem. So there's apparently no relation, but there's a very important idea which we often call the quantum to classical mapping. In the language of field theory, it's also often called the path integral approach, which allows you to make a connection between quantum mechanics and statistical physics. And so this is really why statistical physics is statistical physics is already profound because it describes how, you conventionally learn statistical physics as, how you describe big collections of classical particles, but it can also be used to solve quantum mechanics, and that's, I think, very magical. And I don't know who originally came up with this idea, but Feynman is often given credit for popularizing this idea of the path integral. And so the idea is in quantum mechanics, when you want to calculate, say, a thermal partition function, it's trace exponent minus beta h. So h is this operator, and this trace is over the many-body Hilbert space. And so the idea now is that you can map this to a statistical mechanics problem in one higher dimension. Okay, so I again won't go over the details. You can do it for the Ising model, you can do it for many models. But you can just see it very simply physically over here. So exponent minus beta h is like the time evolution operator. Right? Remember in quantum mechanics we learned the time evolution operator as exponent minus I h t. So it looks like this is a time evolution operator except there's no I. So you can interpret this as a time evolution operator in imaginary time. Okay, so there's a time evolution where you have a state and it goes to some state under time evolution. Right, so this is the time evolution operator. It takes your state, and so your initial state is time evolved by imaginary time beta, and then the time evolution says it's a sum, the partition function is a sum over all configurations which take the initial state back to the initial state. Okay, so there's a very simple physical picture you can make is that you begin with some initial wave function, you time evolve it for imaginary time beta, and then you ask for the amplitude that after this time evolution is still in the same state, and then you sum over all states. Okay, so now the interesting thing is that this time evolution can be related to a classical statistical mechanics problem. Okay, so again, I won't do this. You can do this for the Ising model. You can do it for many models, and actually it turns out to be quite complicated when you go beyond the Ising model. In the Ising model, it's relatively simple, and there's some notes again on that website that I have. It's also there in many books. It's a very classic thing you can do. Is you can show that if you take the Ising model, you take your initial state, which is some set of spins, and then as you time evolve them, these spins keep changing. And so now what you get for this trace exponent minus beta h with a particular state, you can associate with a statistical mechanics problem in one higher dimension. Okay, so this is a very important idea, is that this partition function, so maybe you want to call this ZQ for quantum. Okay, it can be related to a classical stat mech problem in D plus 1 dimension. Okay, so for instance, if you take the Ising chain in 1D, it's connected to a 2D classical statistical mechanics of the Ising model. Okay. Now the weird thing is that this Ising model is not the conventional Ising model, because notice time and space are very different in this Hamiltonian approach. So it maps to a very anisotropic Ising model. But again, when we reach the critical point, because you have a floater fixed point, it turns out this anisotropy is one of those irrelevant directions you can forget about. And so when you study the wave phase transition in this model, it maps exactly to, in D dimensions, it maps the D plus 1 dimension classical Ising model.
I have a question.
Mm-hmm.
If the quantum frustrated speed model,
Mm-hmm.
if we consider such a model, the Boltzmann weight of classical D plus 1 dimensional moment space, sometimes it should be negative. So
Yeah.
It is a good thing.
Yeah, so that's a very good question, and that's going to be exactly the focus of my talk. Is that, of course, in this particular example, it turns out that the weights of this classical problem are all positive, And so you can interpret it simply as a classical StatMech problem. And so the rest of the talk is going to be exactly in situations where that's not possible. And those are the most those are the most interesting ones. So that's a great, very good point. So that's a good point that I didn't. So it's true that if you take this quantum problem, it maps to a classical problem in d+1 dimension. Of course, the classical problem is not guaranteed to have positive weights. So by definition, classical statistical mechanics, all your configurations have positive weights. So I should say it doesn't technically always map to a classical statistical mechanics problem, but in many cases it does. It does map in the Ising model. Okay, so in the Ising model, what you get is a d+1 dimensional anisotropic Ising model. Okay, so you can write a formula down exactly. So you take your original Hamiltonian in d dimensions, right? And I'll often just drop all the signs just to make it look neater, but I think you can remember where the sums on lattice sites are. So this is defined on a L to the d lattice. And now you can relate this to model in which it's an Ising. Okay, I said I won't put the sums, but then I put the sums here. So this is a space-like coupling between sites I and j, and this is a time-like coupling between sites on the same site. And so this anisotropic Ising model is defined on a L to the d times at a tau lattice. So yeah, I'm imagining that I'm discretizing time. And then of course, to actually simulate the Hamiltonian, you have to take a particular limit. Okay, so the limit is defined by taking jx go as epsilon j, and j tau goes as log h perpendicular divided by epsilon. Okay, where epsilon is beta divided by the number of time slices. Okay, so if you take this limit, so basically you have to, in one direction you have to make more and more time slices, and you have to make the coupling actually infinitely strong in the time direction, and in this direction you make it weaker and weaker, so it gets smaller. And so if you take this limit, then you actually study the original Ising model. Okay, so correlation functions in the original Ising model actually connect to correlation functions. So if you measure space-like correlation functions, equal time correlation functions, they map to correlation functions in this direction, and then you can measure time-displaced correlation functions, and they're like correlation functions at different points in the time direction. Okay, so there's a very nice mapping between all of this. Okay, so all of this is very well known, and at this point it seems like, okay, well, there's nothing interesting in spin models because they always connect to classical models. So I should say, of course, that all of this is only true for the ground state property. Okay, so it's only true that the ground state property, so remember when you make beta it goes to infinity, this partition function is dominated by the ground state eigenvalue. Even for the Ising model, there are properties of the dynamics which are interesting and which are still debated and not completely solved. But at least the ground state you can solve and study completely using this trick called the quantum classical mapping. Okay, so now I want to come to Professor Harada's question, which is that I made this assumption that this statistical mechanics problem has positive weights, and that's not always true. So what do you do then? So let's study some examples where it doesn't have positive weights, and so those are the problems I'm most interested in. Okay, so this set of problems we now understand very well, and we're most interested in these problems where they don't have positive weights.
Maybe I can make a comment which is somehow between these two cases. So in this case you mapped it to the same model in one higher dimension, but you can also have cases where you don't have any signs, but you map it to not the same model in a higher dimension, but to some completely different model, right? Some model that may not be very natural from the classical StatMech standpoint, right?
Yeah, that's.
And then you have many more interesting things than what you get in that case.
Right. Yeah. So.
For example, when we study deconfined criticality quantum spin models, it maps to some very strange classical StatMech problems, right?
Right, yeah. So, I mean, there are two ways to think about it. One is, yeah, whichever way you think about it maps to a state change. So what I'll talk about is how you can map it in which, you know, so you want to map it in a way in which the, you know, the classical fields you have over here describe the slowly varying order parameters in the quantum model, right? So here the slowly varying thing is the Ising model itself, and so even for the Heisenberg, maybe we'll talk about. But you're right, of course, that there's one mapping which is simple, and then there are mappings which are more complicated.
Even classical models, you can map, like Ising model, spin model, you map to cluster model.
Right.
Yeah, of course. So there are many ways to rewrite Ising, all statistical mechanics by duality.
Like classical Heisenberg model or Owen model maps to loop model.
Right.
Right.
Yeah, so I mean, I of course I'm simplifying the story a little bit to tell my story the way I'm saying it, but there's obviously a lot more to this. I mean, it's a very big topic. So let me just study a very simple example now of how this program can get more complicated. Okay, and that is one thing that I want to talk about a lot today is topological terms. Okay, so let's study the first example of this, which is the spin half XY chain. Okay, so we just studied the spin half Ising model, and there we showed, okay, everything goes through, it's just an Ising model in one higher dimension. So now let's take it to the next level of complexity. Let's imagine that you have the following model. Okay, so these are again quantum spins. So this is called the quantum XY model. We're imagining you have spin 1/2s. So, you know, of course you could define it for any value of spin, but we're defining it for spin 1/2. It's a two-level system, and this is what is Hamiltonian is. Okay, so naively when you look at this, you may say, so what do you think the classical statistical mechanics? So we can do the same thing, right? We can take this model and then think of this time evolution operator, add another dimension, and we can get a classical StatMech model, right? So what would be the natural guess for what the classical StatMech model is? Okay, so imagine that we do this in one dimension. We take the XY chain. So very naively you say, that, well, actually, when you do this, it maps to the classical XY model in two dimensions, right? And it turns out that's not quite correct. Okay, and I think the person who first realized all of this was Haldane, and it was part of what he got the Nobel Prize for.
But actually, if you just map it in the most trivial way, which was first done by Professor Suzuki in Japan, right? I mean, you just get an Ising-looking model in one higher dimension, but it's not an Ising model. It's the six-vertex model, right? In that.
Yeah. So that, of course. So there are different ways in which you can do this mapping. So the problem with so it's true. It's just like how you're saying the antiferromagnet also maps to some loop model, just like the six-vertex model. But in that language, it's not simple to write down what the order parameter is. Like we expect, for example, that there's an XY order parameter, XY order. So here, for example, the Ising order parameter is related very simply to this classical StatMech model. In the six-vertex model, the XY order parameter even the symmetry of XY order is actually not obvious. If you look at the six-vertex model,
it's not. But I mean, if you just go through the steps, you can do it very exactly. I think what you want to describe now is when you start to make some more effective theories. You want to have your degrees of freedom being like classical degrees of freedom, even if even if they're not, right?
Well, I think what we want to do is we want to sort of find a way to connect. So maybe it goes back to the first part where I said that there's this very powerful way in which we have to analyze classical StatMech models, and so we would like to connect these to classical StatMech models in one high dimension. For example, if you have that six-vertex model, I don't know how you would do a renormalization group transformation related to things that we already know about the XY model.
But you can do the Kono Monte Carlo, for example. You can do calculations with it. Right?
Yeah, absolutely. So that's exactly the point at the top, is that there are two ways to think about it. In the field theoretic way, we don't like to do that,
Right.
but in the numerical way, we like to do that. And so that's exactly what we're trying to do here. That's what the talk is about. Is that when you do Monte Carlo, you like to think about these different representations because it allows efficient simulation. In fact, trying to map it to XY model, you get complex terms in this. And you can't do Monte Carlo on it.
Right.
And so this is the amazing power of Monte Carlo, is that you can study something that looks like it has a sign problem in another representation. So for people who come from field theory, that representation is very natural because it then connects to all the, costless, Thouless, it connects to everything we know about XY models.
But it has to do with the choice of basis you do when you do the mapping too, because what you will talk about now, I guess, is when you use this over complete coherent state basis and so on, right? Instead of just using the naive basis as we do in QMC.
Yeah. So I mean, I think what you're saying is they both have power to do different things. I mean, so the advantage of doing this is it connects to this classical field theory, and of course, if you want numerical simulations, is not very helpful. You'd rather do the word line representation. So they both, and so what we want to do is, but it's very interesting because some things are easier to analyze in one way, and it's very hard, as you know, to translate from that language to the other language. I mean, this is very complicated, right? Because in this language you can draw renormalization group flows, and then what we want to do is we want to understand what the consequence of the renormalization group flow is on this model, on which we can obtain numerical data using these methods. Okay, so naively you would think this maps to an XY model. So as Anders says, of course you can map it to various statistical mechanics problems in one higher dimension. But most naively, because there's this U1 symmetry over here, just like you saw on the Ising model, you might think that you can just take XY spins in 2 dimensions. Okay, and that's almost correct. The part that it misses is because this is a spin half, we know that if you take a spin half and you rotate it by 2 pi, it acquires a minus sign. Okay, so when you take classical StatMech XY model, that's not true. Okay, so you have to put that in. And there is a systematic way of deriving this. I'm just, in fact, it's up there on the website, or it will be. I mean, it's there in another folder, but I'll link it so that you can have access to it. But the point is, if you try and do this, it is a StatMech problem in one higher dimension where you have this theta variable. But this action that you get is unconventional. Okay, and it's unconventional for very interesting reasons. Okay, so the first term over here is just the usual XY model. So like, if you read Kostelis, Thouless paper and all, of course, in the time direction they also have a cosine coupling. But here, of course, in the usual way of thinking of a classical StatMech problem, there's a lattice in space and in time. And so if you discretize this time derivative, this gives you exactly the cosine term in the imaginary direction. Okay, but the interesting thing is that this term is usually not discussed. Okay, when we discuss the XY model, this term is not discussed. And this term, so what is NJ? So maybe I should give you some more details. But just please stop me in case I'm not explaining everything clearly. So when you solve this problem, you have to solve them with a boundary. So theta is theta is not a compact variable that goes from 0 to 2 pi. It goes from minus infinity to infinity. Okay, but you have to solve it with a boundary condition that theta j beta equals theta j 0 plus 2 pi nj. Okay, so the problem is that you like to define it as a variable that goes from 0 to 2 pi, but if you take the time continuum limit, you can't do that anymore, because you want in time for it to move very smoothly, but when it crosses 2 pi, it jumps, when it crosses 2 pi, it jumps from 2 pi to 0, right? So then you can't define a derivative. So to solve this problem, what you do is you sort of, if you like, unwrap this from 0 to 2 pi. You just define it from minus infinity to infinity. But then you require, because it has to come back to itself, remember that was the condition we had for the partition function. When it comes back to itself, theta has to change by 2 pi times an integer. Okay, so if you imagine that theta begins somewhere over here, so say this is 0, this is 2 pi, this is 4 pi. You can do whatever it likes, but at imaginary time beta, it has to be an integer multiple of 2 pi, so it can be either up or down. And the number of times that integer is what I call nj. Okay, so the simplest situation is nj equals 0, which means that it comes back exactly to that value that it began, but it doesn't need to do that, it can come over here. Now the interesting thing is, if it comes over here, this particular xy spin has gone and made one 2 pi oscillation, right? And because of that, I now have to give it an exponent I pi. Okay, so this is the very phase of a spin 1/2. If you take a spin 1/2 object and you rotate it by 2 pi, you have to put a -1. And it turns out that these very phases that you can derive just naively by thinking of adiabatic transport also always appear in the path integral. So again, you know, I've heuristically explained why this is over here, but you can do the systematic derivation. You can start with equation number 1 and do the derivation and arrive at this explanation that's up on the internet. Okay, so there are various ways to do it. You can do it by spin coherent state, but there's also a simpler way you can do it with just a quantum rotor. So now, you know, as of course, as Anders pointed out, there's different ways you can map this to various different StatMech problems in one higher dimension. This is one of them. And this has the virtue that it is very close to something that we know and understand very well, which is the XY model, but it has this perturbation in it. And so now our goal will be to understand what the effect of the perturbation is on the XY model. Okay, and it turns out that this actually gives us a lot of insight into the problem. And then of course we'll want to also simulate the model and try and understand the connections between the insights we can get from field theory and from the lattice model. Okay, so any questions about this? Okay, so this is the simplest example of what is called a topological term. Okay, it's topological in the sense that if you take a configuration, or you take basically a single spin, and you look at its trajectory in imaginary time, say it's this, then there's nothing you can do to change what this term is, right? So this is nj, you can change the trajectory slightly, you can actually even change it a lot, but there's no way you can go from here to changing the value of nj, right, without doing something very dramatic. And so that's why this is called a topological term, because for a particular trajectory, it's a topological invariant. Okay, so this is the simplest example of a topological term. We'll study more sophisticated examples as we go along in the rest of this lecture. So, but now let's try and analyze what this term does. And I think this was already done by Haldane. It's sort of hard to understand his original papers, but it's clear that he understood the implications. Okay, so the first thing is that it's sort of, so we know how to, so if you've studied Kosteles-Thouless work, we know how to analyze this problem very well in terms of vortices, the Sine-Gordon model, and we'll talk about that in a second. But the minute I put this in, I'm sort of in trouble. Okay, because first of all, as Kenji pointed out, that now when I exponentiate this, I have configurations with negative weight. So I can't even think of it as a StatMech model. And the other problem actually is that the coefficient of this, which is pi, cannot be tuned. So normally when you do renormalization group, you can set some parameters to 0, you can allow them to be small, but there's no, the thing is, by symmetry, I'm forced to have this coefficient to be 0 or pi. Okay, so in this particular case, once it's pi, it can't really move. And so it's hard to deal with this in any kind of perturbation theory. Okay, so this is the complexity of topological term which we have to deal with. Okay, so here's a very simple argument for what this topological term might do. So it turns out in one dimension, we can actually almost completely solve this problem, and it's very interesting and very instructive. You learn a lot by actually understanding the effect of this. Okay, so let's first forget about this, and let's look at this. This is the XY model. Okay, so are you all convinced this is the XY model, or any questions about that? It's not the conventional way in which you write the XY model. It's the XY model in which you've taken the time continuum limit in one direction. So in one direction you're on the continuum. So if you want to think about your configuration space, it corresponds to this. Right? So instead of a lattice, it corresponds to having a continuum in time. And so you have to specify this function, theta as a function of time. So this is time, and this is theta j. Right? So theta j is a function of time. And then, of course, it can vary as much. So it has to be smooth when it goes in time. But from next side to next side, it can vary as dramatically as you like. It doesn't matter. Just like any lattice model. Okay, so imagine you're doing all the sum over all these configurations of theta subject to this boundary condition. Okay, so you can show very easily that if you neglected this term, this is exactly the XY model. There's no difference between this and the XY model. It has exactly the same.
I'm sorry, I can't see how the J is related to the S theta. Where does the J come in? The Hamiltonian has minus J summation over.
Oh yeah. So it's some rescaled version inside over here. So you know the Hamiltonian, as far as the ground state is concerned, J perpendicular plays no role, right? It just sets the energy scale for the Hamiltonian. I mean, you could set it to 1 if you like to. So there is a little bit of a complexity when you go here. Is that there is some quote-unquote field theoretic manipulation that takes place. So it's not possible necessarily to map a particular value of J perp to a particular value of K. All we know is that if we add, it's like we're adding irrelevant operators. So if you add more terms which maintain all the symmetries of the XY model, and you look at a phase diagram, you expect the phase diagram to be the same as the phase diagram of this StatMech model as you vary K. Okay, so it's not as exact. In the Ising model, it's very exact. You take the Hamiltonian and you take that anisotropic model and you make the anisotropy smaller and larger in directions, and then it maps, you'll get exactly the same number. Here it's not that simple. You don't get, I mean, there's no way, I mean, the only way to do that is the way Anders says, that you map it to this 6 vertex model. Then you can do it sort of exactly. But when you do it like this, you're making some approximations, you're making some, the approximations are believed to all cause only irrelevant changes. So it doesn't change the nature of the phase diagram. Okay, so that's why this is a little bit, it has to be done responsibly. It's sort of hard to, it's easy to make mistakes, and because there's a lot of arguments that go in. Okay, so now the question is, how does a vortex look in this configuration? So we all know how the vortex looks on a lattice, but how does the vortex look in the language of this theta j? Okay, so there's a very nice picture that you can see how a vortex looks over here. So basically what a vortex looks like is what nj tells you is the number of times this particular guy winds around in imaginary time. Right? So what happens is that if you have a vortex at a particular space-time location, nj has to change by a unit. Okay, so the simplest vortex you can have is when nj is 1, 1 and goes to 0, 0, 0. Okay, does this make sense? So that means that if I look at theta over here, it's winding around once when it comes back over here. It's winding around once when it comes back over here, but when it crosses the vortex, it stops winding. Okay? Because remember, if you draw a loop around a vortex, it has to wind around once. So all that winding now is happening on one side. Okay, so in this language, this weird language where we've taken this continuum time, this is how a vortex appears. Okay, so now because the vortex has such a simple structure, so basically a single vortex will always correspond, so you could have 55, 55, and this could be either 54 or 56, say 56, and that's a vortex of strength 1. If you made a vortex of strength 2, it would go from 55 to 57. Right? It has to jump by 2. Okay, so it can be anything, but let's assume that the configurations are simple, so it's 1, 1, 0, 0, 0, 0. Okay, so now what Haldane said, or at least the interpretation that we give to what he said, is that you evaluate the sum, and you get a particular, so you want to know the weight of this configuration, so you evaluate this whole thing, which is an integral and a sum, you do the whole thing, and then you take all the nj's and sum them up. Okay, so now what Haldane said, which is very interesting, is imagine that you take this configuration and you freeze everything else, and you move this vortex over by one lattice unit. Right? So usually if you had a if you had a gas of vortices, you have one vortex and you move it by one lattice unit, you don't expect the action to change very much, right? Because the configurations are very smooth, and so changing something by one lattice spacing doesn't change it very much. But you see over here has a very dramatic effect, because if I shift this guy now by 1, suddenly 1 nj, which was 0, became 1. So I get an e to the I pi. Okay, so what that means is that if I shift the vortex by one lattice spacing, this exponent minus s theta changes sign. Okay, so this is a very important idea, is that the vortices, so some way, the way the field theorists will say this is the vortices carry momentum. Okay, so they actually carry momentum pi, because every time they translate by one lattice spacing, they get a minus sign, which is exactly what happens at momentum pi. Okay, so what this tells you is something very interesting, is that a single vortex cannot exist in the system. Okay, because imagine I'm summing over all configurations, and I have a single vortex. Now, the configuration where this vortex is translated by one lattice spacing will also occur with equal probability, because basically the action part is going to be about the same, because I've only translated this one vortex by one lattice, so these differences won't change very much, but this will change by a minus sign. So the vortex at vortex over here and the vortex translated over here will actually cancel each other, these two configurations. Okay, so this is a very important idea. And so in this particular case, we can actually evaluate this sum. Right? Basically what it does is every time you have a vortex, an isolated vortex. Now of course notice that if the vortex was a vortex of strength 2, right, then you wouldn't have this problem. Because now if I switch this from 0 to 2, I just change this by exponent I 2 pi, which is 1. And so if I have a vortex of even strength, I don't have this problem. I only have this problem if I have a vortex of odd strength. So we now reach a very interesting conclusion, that actually this XY model maps exactly to the XY model, except it only has double vortices. Okay, so that's a very interesting thing. So in the usual XY model, you allow all vortex configurations to come. Now you only allow double vortices. Okay? So it's an XY model with double vortices, and it turns out that, and we'll do it now, that the whole field theoretic machinery works beautifully to solve this problem. So when I had the I pi, I couldn't do it because I didn't know what it was. But now I've shown that the action, basically, forget about this I pi, but I just have to remember that when I sum over my configurations, there should be only even strength vortices. Okay, so it's a weird StatMech problem. So it's the XY model in 2D with double vortices. Okay, so now we're left with the problem of analyzing this problem. So for those of you who are familiar with Kostelis-Thouless argument, it's very easy to proceed and analyze this. And I'll reproduce some of that over here in a second. So I don't know how we're going to do with time, but I'll try my best to put it in. Okay, so the notes are up also, you can read about it. Okay, any questions about this? Okay, so this is a very simple example of how when you take a quantum spin system, you can almost map it to a well-known classical StatMech problem, but then these are often called Berry phases, right? I mean, because it's the Berry phase of a spin 1/2. It leads to a complexity which puts some weird constraint in our problem. But the nice thing is now this weird constraint we can actually deal with, because you don't have any of this topological terms anymore. You just have to analyze this problem. Okay, so I want to talk about one more example, and then we'll go and analyze this XY model in detail. Okay, there's a trick called bosonization which will help us. It'll give us some more information than just this. So we studied the spin half XY chain, and we showed that it maps to, in one higher dimension, to the XY model with a Berry phase term, and we saw that we can actually evaluate this Berry phase sum and show that all this does is it forces your vortices to be doubled. So now you could ask, what if you do the spin-off Heisenberg chain? Okay, so we went from Ising to XY to Heisenberg. Okay, so this is you know, Haldane's maybe most famous work. And this calculation is slightly more complicated than the previous one, but it's there again in all the books. Okay, so now again what we want to do is we want to take z, q, which is trace exponent minus beta h, and we want to do all our steps, the Suzuki step where you break this Hamiltonian up into small time evolutions, insert a complete set of states, and now in your imaginary time, what it consists of, the spin, remember, so the xy model had a 2-component vector. The spin itself consists of a 3-component vector. Okay. In fact, we typically work in terms of what is called the nail vector, okay, which is the staggered sum of the spins. Okay, so again, I don't want to do these steps over here because this is too explicit. So I'll just write the result down for you just like I wrote this result. So in this case, this partition function becomes a classical stat-mech problem in one higher dimension. But again, it has a topological term. So it turns out these topological terms are very common actually. Once you take a quantum Hamiltonian, you try and write a path integral, you almost can't escape it. The Ising model is very special in which the sense that it doesn't have it. In all the other cases, it plays a very important role. And really the goal of what we're doing is to understand the effect of these topological terms in higher dimensions. It turns out in one dimension it can be analyzed quite completely, but in higher dimensions it's very poorly understood, partly because there's no way to solve. So in 1D there's all kinds of tricks. There's conformal field theories, there's bosonization, there's beta ansatz. But in 2D the only thing we basically have is Monte Carlo. Right? I mean, at least to study critical systems. And so what we're trying to do exactly is understand the effect of all these terms when all you can do have is Monte Carlo. Okay, so that's what we'll come to at the end. But let's just talk about this Heisenberg chain. It's very important. So you take the Heisenberg chain, exponent minus beta h. So now you have this nail order parameter, and you integrate over the nail order parameter. So again, it's in one higher dimension. If you take the, let's say you just take the chain, then you get a 2D, and you have the nail order parameter is, we call it a O3 vector, because it's a 3-component vector. And so now you have a 2D configuration of these 3-component vectors, right? And they all point somewhere or the other. And you want to write down what the action is for them, right? So the simplest term you can write down is the so-called gradient term. And that's what people basically thought would happen. But in his seminal work, Haldane showed, just like we saw in the XY model, which is very simple, but here it's a little more sophisticated, that there's an extra term, a topological term, which depends on the value of the spin. And in fact, it takes this following form. Okay, so S is the value of the spin. So for spin 1/2, it's 1/2, and this coefficient is pi. Q is something which is called various things. It's called the Skyrmion index or the Pontryagin index, and basically it is a topological charge of these configurations. Okay, so if you give me any configuration, any smooth configuration of a 3-component vector in 2 dimensions, I can associate a topological charge with it. Okay, it's very similar to if you just give me 1 dimension, and that's what we used in the previous part. If you take the XY model and you give me any smooth configuration, there's a integer topological charge you can associate with it, which is the winding number, right? Right. So it's very much like the Mobius strip, right? You take a strip of ribbon and you seal it, and if you twist it, then you put one topological charge. You can twist it clockwise or anti-clockwise. So this topological charge is an integer because you can twist it q number of times. So the XY model is a 2-component object, and the physical space is 1-dimensional. So it's a well-known result in topology, is that if you increase the number of components and you increase the number of dimensions one at a time, you always get a topological charge which is an integer. Okay, so in this case, you have one extra dimension compared to that, and you also have one extra direction for the spin, because the spin is 3, and so there's again a topological charge. Okay, there's a formula you can write down for it. It's a famous formula. I'll just write it down. Okay, maybe you've seen this formula. It's very important also in the quantum Hall effect. It's called the Skermion number. Okay. Okay, and you can prove exactly that this number is always an integer. Okay, so this is a very interesting problem. Now you have to analyze this problem. Okay, and unfortunately, there's nobody really knows how to analyze it. Okay, so the interesting thing is, it goes back to what Anders was saying. Actually, the only way we know how to analyze this is we can solve the spin Hamiltonian. And by knowing the phase diagram of the spin Hamiltonian, we can infer what the phase diagram of this model is. Okay, unlike the XY model where we could show that it's double vortices, over here there's no simple story in which this simplifies to some other statistical mechanics model we know. So that's why when Haldane did this, the fact that you could solve the one-dimensional Heisenberg model by beta ansatz was very important. Okay, and so what we're going to talk about today is how, because we can do Monte Carlo in 2 dimensions, we can answer the analogous questions in 2 dimensions to answer, what kind of phase diagrams these field theories can have.
Excuse me?
Yeah.
Is there any direct method for dealing with this XY to the system with constraint, a double vortices constraint?
Yes. I'll talk about that.
Oh, okay.
Yeah.
Thank you.
There's a way where you connect to a sine-Gordon model.
Okay. I see.
I'm going to talk about that next. Yeah, thanks. That's a good question. So this, there's a way of analyzing completely, analytically. This, on the other hand, there's no way of doing it, except that Haldane knew basically that spin half, had this by beta ansatz, and then he knew spin 1. I think AKLT had shown that there's a gapped wave function, so he put all of that together. And so there's one important thing actually. So you could say, why is this even useful? Okay, so the one useful thing actually that comes out of this mapping, because you might say, first of all, okay, so this mapping is useless because you can't solve it, but actually it is useful. One way in which it's useful is you learn that if the spin actually has an integer value, you get I 2 pi q. Okay, an exponent I 2 pi q is +1, and so this maps exactly to the sigma model in 3 dimensions. So whenever you have integer spins, the sigma model, and we know how to solve the sigma model. Remember, that's the whole idea. So using renormalization group, this can be solved. I think it was solved originally by Polyakov and Wiegmann. And they showed that this thing is always gapped. Okay, which is why for integer spins, the spin chain goes into the gap, which is called the Haldane gap. Okay, for half integer spins, then you get exponent I pi q, and then we don't know how to solve it because you can't neglect this anymore. And then we rely on the fact that the spin half chain can be solved to guess what happens to this field theory at a topological angle of pi. Okay, so the spin chain in some sense is very, very important in analyzing the field theory. So we began to derive the field theory to solve the spin chain, but in the end it turns out the spin chain is the one that actually allows us to understand this model. Okay, so basically Haldane conjectured, which is called the Haldane conjecture, that all integer spins go into the gap state, and all half integer spins. So remember, if you have 3 halves is 1 half plus 1, and the 1 you can forget about because you have exponent I 2 pi q, and so he basically conjectured that all half integer spins are in the same phase. Okay, which is not obvious, but that was his famous conjecture. Okay, so finally, because this will be important for what I'll talk about in the end, after Haldane did this Nobel Prize winning work, there was another very important set of work by Affleck when people had just discovered conformal field theory, and they realized that the spin half Heisenberg chain, there's a different way to write this field theory. Okay, and this field theory is called the SU2 level 1 Westermino-Witten theory. The action of this theory is, so again, the technical details of this are not important, and I can't say that I completely understand all the technical details myself, but I want to emphasize some things for you. So there's a topological term here which is called the West-Sumino. I've written it down over here. I don't think it's very helpful unless you okay. So so now interestingly, this phi is a 4-component object. Okay, so remember this snail vector was a 3-component object. The phi is a 4-component object which is nx, ny, nz, and the 4th component is the dimerization of the spin chain. Okay, so this is a really amazing result. It shows, again, this goes back to the idea of emergent symmetry, that this model seems to have O4 symmetry, right? Because you have these 4 guys over here, and it turns out this topological term is also invariant under rotations under O4. And the 4th component is the VBS order parameter. So this is very, very surprising because it shows that you took the Heisenberg chain, and there's a VBS order parameter, so I'm assuming you're familiar with it. Maybe Anders mentioned it the other day. So in one dimension, the VBS order parameter measures dimerization along the chain, and the nail order parameter measures spin fluctuations. And so you might think that these are completely unrelated to each other, but what this field theoretic rewriting shows you is that they're actually connected by a symmetry. Okay, so this is an example of a very non-trivial emergent symmetry. Okay, so this turns out the spin chain has a huge amount of symmetry. So it's sometimes called SU2 cross SU2 symmetry. And you can study this in the spin chain. Okay, so then there's some details about a marginal operator that comes here, but if you're interested, we can talk about that more. And actually come up when we talk about bosonization. So, okay, so this is basically what we know about spin chains, or there's some of the things we know. And what we want to do is understand how this generalizes to 2 dimensions. So that's the main discussion of what we talk about. So, okay, I have an hour left. And I had notes about the bosonization of spin half chain. So I think it was to answer Naoki's question. So maybe I'll do that very quickly. And then I'll come back to this whole issue. Okay, and it turns out that this whole issue is very closely related to deconfined criticality, because it turns out to, all of this field theory becomes in 2 dimensions magnets order. So if you just take the Heisenberg model, it orders. But if you take it to a critical point of VBS, then exactly these kind of field theories, which are generalized to 1 higher dimension, seem to be one description of these critical points. And it's it's all based on conjectures which haven't been proven, and that's why the numerical simulations that all of us are doing are so important in establishing this very interesting conjecture. So I'll tell you some of the conjectures.
So it's here, can I ask a question maybe not very related? So I couldn't forget this Gaussian number is integer. So does it matter it's open boundary condition or periodic boundary condition?
Yeah.
Not related to what you're talking about.
No. So technically, it's only an integer if you have closed boundary periodic boundary. So technically, the integers. So the physical space can be a torus, and technically the way mathematicians usually define it, it's a sphere. For us, it's a torus, and it turns out that whether you choose a sphere or torus, you get an integer. But if you cut the torus open, then it doesn't have to be an integer anymore. So statements for periodic boundary conditions. Periodic boundary conditions, or you can have boundary conditions where at the edge you require all the spins to be up.
To be up.
That'll work too. So you can have hard boundary conditions, periodic boundary conditions. But if you just have open boundary conditions fluctuating, that's not quantized. Yeah, and that's important. That's it tells you that you can have edge modes for the spin 1 chain. That follows from all these things. Right, because if you could just drop this, so in fact it tells you that you can drop this for the spin 1 chain only with periodic boundary conditions. If you have open boundary conditions, you can't drop it, and this is exactly what creates the edge modes of the spin 1 chain. So, okay, so now, okay, I wanted to do this microscopic. Okay, so it turns out again in 1 dimension we can do a full analysis, including that problem that I raised of XY model with double vortices. We can't do this in 2 dimension. In fact, that's what the deconfined criticality, in some sense, that's exactly what the deconfined criticality problem is. So let me show you how it works in 1 dimension, because it's very useful and it shows you how people got the idea for 2 dimension. It's all based very much on their understanding of 1 dimension. Okay, so I'm going to be very quick, but stop me again if there's anything I can explain. So you take the XY model, right? And now there's a trick called the Jordan-Wigner transformation, which I'm sure you're all familiar with. Basically, the idea is that you take the spin up and down, you map it to a fermion, but you have to include the string of operators. So if you do all of that, I think it's very well known. So it's there in my notes, but I won't do it over here. Is this maps exactly to the problem of free fermions in 1 dimension. Okay, so at half filling. Okay, so is this? Should I need to explain this to you? Just tell me if I need to explain it, because I'm going to go faster now. Okay, so you have this basically the spin chain is at half filling, and so now what you do in this is that you can basically linearize it around this point, and you get a 1-dimensional Dirac equation.
So this is for open boundary conditions. So for pure boundary conditions, you have a large one.
Yeah, so there's a subtlety. Yeah. So imagine it's open boundary conditions, an infinite system. So there's a subtlety that when you do it with periodic boundary conditions, there's you put a flux in the ring, depending on the parity. But so let's imagine that I'm doing with open boundary conditions, but imagine that they're very large, so I can still define momentum. Okay, so so you linearize the system, and these are called the right movers, and you linearize over here, it's called the left movers. And so you get this free Dirac equation, and you can use the Dirac equation to describe all the correlation functions of the XY model. Okay, so long distance is described by the Dirac equation. Okay, but of course, so it's very special that the XY model actually maps to a free Dirac problem. If you add any perturbation, so what I mean by perturbation is I mean something which maintains the XY symmetry. Okay, so the most simple example of a perturbation is to add a term which is okay, but you can add many other terms. And now when you try and do the Jordan-Wigner transformation, you won't get a free problem anymore. You'll get a problem of interacting fermions. So now you could ask, what is the continuum limit of those? So what additional terms do they bring in? Okay, so the terms could look like psi right dagger psi right, psi left dagger psi left. So this, so I should first point out that this problem has a very special symmetry, right? So this conserves the number of right movers and left movers. Okay, so this is a very special property of the XY model. The XY model only has U1 symmetry, so you expect only one conservation law. But somehow this free fermion fixed point has 2 conservation laws. Now this type of interaction preserves the 2 conservation laws, because whenever you destroy a right, you create one. So this has this. But now there is an extra term you can write down, because you're exactly at half filling, and it's called the Umklapp term. So you write it like this. Sorry. Okay, so what it does is it takes 2 fermions from the right and moves them to the left. So naively this looks like it violates momentum conservation, but because you're exactly at half filling, this is allowed because of lattice momentum conservation. Okay, so now this is very interesting, because this, in this language, is exactly where double vortices come from. Okay, so the fact that there are 2 psi r operators and there are 2 psi left operators. So again, if you were at some other filling, like 1/3, then you'd require 3 right operators and 3 left operators. But because you're exactly at half filling, you allow 2 right operators and 2 left operators. And each of these terms is like the introduction of a vortex. And so when you put both of this, it becomes like the double vortices. Okay, so the way you can see this again is by there's a trick called bosonization where you take this Dirac fermion and you rewrite it in terms of boson field. And so the Hamiltonian in the boson language, and again if you're not familiar with this, this is a chance to learn some of the physics is quite simple. I mean, I think you can learn about this stuff. Okay, so this is how it looks. So theta is called the spin field and phi is called the vortex field. This is exactly what happens in the XY model. It's very similar to the XY model. Now in the XY model, what you have actually is instead of cosine 4 pi phi, you have cosine 2 pi phi. Okay, so this guy is the fugacity of double vortices. Okay, so in the normal XY model, you'd have lambda 1 cosine 2 pi phi. Okay, so the only thing that changes so exponent I 4 pi phi is the operator that creates double vortices. Okay, and lambda 2 is the fugacity for it. So basically all you have to do is, if you want to analyze the problem, the XY model with double vortices, is you have to take the XY term and instead of adding a cosine 2 pi phi, you add a cosine 4 pi phi. And in one dimension, it's known very well how to solve this problem. So in 1D, it turns out that you can solve the problem of double vortices completely. So now you have two parameters, you have k and lambda 2, and you can draw a renormalization group flow for it. Okay, this is there in Subir Sachdev's textbook. That's a nice place to read Eduardo Fradkin's book. And I also have notes on it on my webpage. So maybe this got technical very, I mean, unless you've learned some of this stuff before, it's hard to learn it now. But what I'm about to draw, I think you can all understand, is so we have basically shown that this XY model, if I add some perturbations to it, is described by an effective field theory that only has two parameters, lambda 2 and k. And so now what we'd like to do is like to study the renormalization group flow in lambda 2 and k space. Okay? And then what we want to do is we want to then connect to the phase diagram of the XY model, because that shows us how we connect field theory and Hamiltonian field theory with Hamiltonian quantum problem with field theory. Okay, so I put so this flow actually turns out to be very similar to the XY model. So this change of 2 pi phi to 4 pi phi, which goes from single vortices to double vortices. So of course, if you add lambda 1 cos 2 pi phi, this is much more relevant than this, and this dominates. Okay, but as we argued in the XY model, this term is forbidden. All very similar things are going to happen in 2 dimensions. That's why it's very interesting to understand this here. This term is forbidden by what we call quantum interference effects. Because remember, if you take a single vortex, you translate it by one lattice space, you get a minus sign, and so you can't have single vortices. But double vortices are allowed. Okay, so now what we want to understand is the phase diagram of this. So the flow diagram of this field theory. And so I won't show you how to derive the beta functions, but it's identical to what you do for the XY model. So it's there in many textbooks. But the idea is that if lambda 2 is 0, then you have a Gaussian field theory. And this Gaussian field theory is basically a fixed point always. Okay, so there's a line of fixed points along lambda 2 equals 0. Okay, so if you sit at these fixed points and you look at the spin correlation functions, they decay as a power law. The power law varies as you change k. So now what we want to ask is that when you take these fixed points, if you now introduce a small lambda 2, is it going to be relevant or irrelevant at the fixed point? Okay, and so again, I don't want to go into the details of derivation, but it's very well known by very standard methods. You can show that lambda 2 will start to become relevant only when k is smaller than 1/2. Okay, when k is greater than 1/2, what will happen is you flow back to this value of k. Okay, now when k is smaller than 1/2, lambda 2 is relevant, and so you go off over here. So this is a very famous flow which is sometimes called the costless. It was actually, this was what, it's a single author paper by Kosterlitz, and that's what won him a Nobel Prize. Is exactly studying the flow in this. I mean, I think you can study it in various different, again, like every statistical mechanics problem, there's various ways to write it. But in the modern way, this is the way we study it, with the so-called, so this is called the sine-Gordon model. Okay, so if you had, so we're allowing only lambda 2, which is double vortices. If you allowed single vortices will actually become relevant before double vortices. So the flow would be very similar, except that instead of this phase transition happening at 1/2, it would happen at some other value of k. Now I'm going to show you that the phase transition happening at 1/2 is very, very special. Okay, it's related to the SU2 level 1. Okay, so if you hit this point, you flow over here. Okay, so now the question is that, okay, so if you're in this region, so if you're inside this region, right, you flow to this point. And this point is the so-called power law phase of the Kosterlitz-Thouless model. It just is described by a free boson theory. But now the question is that when you flow off to strong coupling, what does it mean? So normally when you have single vortices, when you flow off to strong coupling, it's the high temperature phase. Okay? But over here there are two separate flows, depending on the sign of lambda 2. So what are these phases? So of course, I can give some interpretation of the phases in the field theory, but now we have to go back to our original lattice model and ask, what is the interpretation of the lattice model when lambda 2 goes to plus infinity or minus infinity? Okay, so for that we again have to use some bosonization tricks. And again, this is there in Subir's book, so I won't discuss it here. But it turns out that the VBS operator, so remember the VBS operator is a thing that oscillates at pi. So the VBS operator and the VBS operator, so it turns out, remember that you have a theory of double vortices. Okay, so let me get to this in a second. This will make sense to you, more sense once I explain this. Okay, so I may never get to the second part of my talk, but I'll just maybe end at some point. Okay, so basically, okay, so what happens? When lambda 2 gets negative, the coefficient of this term becomes very large, and then we say phi gets pinned to the minima of this potential. Okay, so remember when this is 0, phi is fluctuating because there's a gradient term in 2 dimensions, that's not very much, so it fluctuates a lot. But the minute this lambda 2 becomes very large, phi gets pinned in the bottom of this potential. Okay, so you have cosine 4 pi phi, and whether lambda 2 is positive, you'll have the maxima and minima will interchange when lambda 2 changes sign. Okay, and so you can show, again, okay, maybe I'll just draw it here. And if you have cosine 4 pi phi as a function of phi, it looks like this. Right, but this is 1, this is 3/4, this is half, this is 1/4, this is 0. Right, so now if I made minus lambda cosine phi, all these maxima will become minima. Right, and now you can, so you always have two minima, they're either over here or they're over here. So it's very easy to show that when you have these two minima, the VBS operator will be 0, but the Ising-Nail operator will be plus in one and minus in the other. Right? And if I put with a minus sign, these will become my minima. And then, what did I say the opposite way? Yeah, sorry. So when you have these, the minima, 1/4 and 3/4, then you'll get cosine 2 pi divided by 4, which is cosine sine pi over 2, which is 1. Right? So when you have these as the minima, you'll have this. And when you have these as the minimum, and when you have the minus sign, then phi equals 0 is a minimum, and when phi equal to 0, sine 2 pi phi is 0, but cos 2 pi phi is 1. So what we see is that this corresponds to the Ising-Nail phase, and this corresponds to the 1D VBS phase. Okay. So now so this is very beautiful and interesting. That is, you get back the XY model, but with double vortices. And when double vortices become relevant, there are two different ways in which they can become relevant in the lattice model. One is that they can create Ising-Nail order parameter, or they can create a VBS order parameter. Okay. So now, are there any questions? So there's a lot of interesting things to think about. Why is this the single vortex insertion operator, blah, 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 but maybe in interest of time I'll keep moving. But if you have questions, let me know. But let me come to the punchline. So now what we can do is that, remember the first thing I showed you is that we want to connect. So we took a quantum Hamiltonian, we wrote it as an action, we got a topological term. We found out that, okay, the topological term in this case can be summed up completely, and it gives us a new statistical mechanics model, which is like the XY model, but with double vortices. Right? So if you want to study triple vortices, you would just put a 6 over here. It's very simple, okay, to analyze in this. Then we can do a complete renormalization group flow of the field theory. And so now what we want to do is we want to go back and say, what implication does this have for the lattice model? Okay, so the lattice model that I will take, there are various lattice models that you can take, but for one model which we're studying right now is the JQ model, which Anders introduced. So you can study it in one dimension. So you can put a Q interaction between spins. And so this is my students, Nishita, who's over here, and you'll hear more about her work. Tomorrow we're studying this. So basically you imagine that you have this Q term, which Anders talked about. And let's take the XXZ model. So remember, this point is the XY model. And let's say that this point is the Heisenberg model. So there's an anisotropy delta. So let me write the model I want to talk about. Right, so I'm taking a model which is minus J SX SX plus SY SY plus delta SZ SZ. Let me take a plus sign here. And then I'll take Anders' famous Q term. Okay, so now I can just, so of course now, as Anders says, you can take the path integral and simulate this and find out details about the lattice model. But the beautiful thing is that because I can also do the whole field theory analysis over here, I can write down what the phase diagram of the model is, and I can tell you what the phase transitions are, everything, without ever simulating anything. And that's of course goes in one dimension. In two dimension we can't do that. So let's take the Heisenberg model. So first you have so let's begin with the XY model, and this is Q, right? And this is delta. So over here we know that we map to this problem with lambda 2 equals 0 and k equals 1. Okay, so that's something we know from Bosenization. And so now what we have to do, what we imagine is that as you tune your lattice model, you're encountering some tour of this phase diagram, in the renormalization group phase diagram. Okay, so imagine as you change some parameter in the XY model, like say you change Q, you're going through some thing over here. And so now you see that, okay, so for some regions you flow back into K, and then at some point you flow into 1/2, and then you flow into the Ising-Nail phase. So let me draw the phase diagram and I can explain to you how it comes. It looks like this. So this is the Ising-Nail. This is VBS. And this is the XY, sometimes called the quasi-superfluid. So remember, in one dimension you can't have long-range order in the XY, but you can have power law correlations. And this power law varies throughout over here. Okay, so the power law is controlled by one parameter. It's an effective parameter, which is K. So we know some limits. We know at the XY model over here, K is equal to 1. We know at the Heisenberg point from beta ansatz that K is 1/2. Okay, so It varies from 1 to 1/2 over here. And now again we can, so now we can infer all kinds of interesting things. Let's ask about the phase transition between the xy to VBS. Okay, so now we go back to this. So this guy over here is the xy quasi long range ordered phase. And this is the VBS. Okay, so when you transition from this phase to this phase, you must cross this separatrix. Right? This is going back over here, and this is going over here. So now you learn something very interesting, is that when you cross over here, whenever you reach this point, you'll flow back into this point. So it turns out this k equals 1/2 is the same as the SU2 level 1 WCW theory. And so this phase transition that goes from the xy to the quasi superfluid, the VBS, actually is exactly the same as the transition between the Heisenberg model and VBS. Okay, so this is very interesting because it's going to be very different in 2 dimension. In 2 dimension, we'll see that there's some difference over here, but in 1 dimension, this is described by exactly the same fixed point. Now, this also is described by the same fixed point. And then you can ask about this transition between Ising-Nail and VBS. And here you see that to do that, you have to cross this line, right? Because if you're here, you'll flow up to Ising-Nail, and if you're here, you'll flow down to VBS. So this point, this line, is described by continuously varying exponents with k less than 1/2. Okay, so just by this field theoretic analysis, there's a little bit more. I mean, if you ask me all the details, I mean, you can relate them all, but it's a little bit more than what I've said. But let me just show you some things that are amazing. Okay, so I think the most amazing thing about this phase diagram is this phase transition. Okay, so this phase transition, you have 2 order parameters. You have the VBS and you have Ising-Nail, and they both go to 0 continuously as you reach this point. Okay, so this is part of the inspiration for deconfined criticalities. In 1 dimension, you can prove this happens. You know what happens. Now the question is, can this happen in 2 dimension? Okay, and if you look at the transition between the xy superfluid, the VBS is described by this SU2 level 1 WCW theory. So as I told you earlier, the SU2 level 1 WCW theory has a symmetry between VBS and Nail, right? This is O4 symmetry. And remarkably now, what you see is that you are studying a transition from a magnet which wants to be in plane to forming a VBS. But when you reach the critical point, if you measure the Ising correlation functions, right? So the Ising correlation functions don't look like they're part of this phase transition at all because they're not in either phase. They are also critical with exactly the same power law as the VBS and the XY. Okay, so it's because you flow back into this point, right? You flow back into this point. So this is a really amazing example of emergent symmetry in a magnet. And so now the question is, can all this happen in 2 dimensions? Okay, and that's the really exciting question, which we're starting to learn the answer. We don't know yet. And that's what I want to spend the rest of half an hour talking about. So this is where numerics will come in a big deal. I mean, so you can, in 2 dimension, unfortunately this kind of model, you can analyze sine-Gordon model very well in 1 dimension completely. In 2 dimension, we can write down some field theories, nobody knows how to analyze them. But we can do numerical simulations. So it's almost the opposite. In 1 dimension, we guessed everything by doing the field theory, and then we can write down lattice models and say that they have this phase diagram. In 2D, it's exactly the opposite. We only have the lattice model, and we have some field theory, and then we try and guess what its flow is by studying what happens in the model. Okay, and it's difficult. Okay, so that brings me to the end of this part of bosonization. Okay, so let's study. So now very quickly, in 5 minutes, I'll just explain to you what, there were some very important ideas due to Haldane and then Reed and Suchdev and Senthil about how this would generalize to 2 dimensions. So in 1 dimension, we understand very well, you have an XY model with double vortices allowed. And it's very rich and complicated. If you couldn't solve this model, you wouldn't have this field theory, which you happen to be able to solve in 1D. In general, you can't make progress on these problems. And this whole structure that I just erased would be sort of hard to see. Okay, so now the question is, what happens in 2 dimensions? Okay, so the starting point could be, for example, the Heisenberg model, and let's just use as an example the model that Anders spoke about. So I wanted to explain what it is, the JQ model. And so now again we have a model like this, and you can add many terms, whatever you like. And so now what we want to do is, we want to do this quantum to classical mapping. So we want to get a classical field theory in one higher dimension. And now remember, this is just like the XY model, it's not exact. That's why it doesn't matter, because you can add whatever terms you like. I just want to study the effective field theory and what the topology of the phase diagram was. So that's exactly what I did in 1D. Right? In 1D, I could draw the topology of the phase diagram without ever, I could take the JQ model, I can take the J1, J2 model, I can take any model. The field theory gives me a universal answer for how the topology of the phase diagram. Okay, so again, I want to get a field theory from which I can guess that topology. So the question is, again, I want to take Z trace exponent minus beta H. Right, and then I want to get a 2 plus 1 dimensional statistical mechanics model. So it turns out that the problem is very, so again, the XY model is like a 2-component vector in 1 dimension, and now we're going to the problem of a 3-component vector, the Nail order parameter, in 3 dimension. So it turns out it's actually very similar to the XY model in 1 dimension. Okay, so it turns out that this field theory, so again, remember we do these steps, and so this guy can be written as the integral of some field exponent minus S. And S is exactly like the XY model. Basically, remember the only term was a gradient term. But now this n vector also has topological defects, which are points in 3 dimension. And it turns out the analysis is more complicated, but philosophically very similar. Is you take a point defect and you ask that if I translate it by a so you know my spatial lattice is in this direction, and so you ask if I translate it by 1 unit in either the x or y direction, how does it change phase? Okay, and it again changes phase. If you take this model and it changes phase, so that's not encoded in this. So there's some phases over here. Okay, we can call them Berry phases. And so again, what we see over here, this was the result again. All of this was done by Haldane actually. Is that he realized that these phases force this problem to have quadrupled hedgehogs. Okay, so just like in 1 dimension, you have the XY model in 1 plus 1D, the point defects were vortices, and you have to have double vortices because of Berry phases. Now, because of point defects in 3 dimensions, you have to have quadrupled hedgehogs. Okay, so maybe over lunch we can talk about what a hedgehog is and other things. I think I'll just assume that you know, or if you don't, we can talk about it later. You can. So I'm going to be here for 2 weeks. I'm happy to talk to you about this stuff. So basically, you have these point defects, and these point defects are also described by a charge, just like the vortices are described by an integer charge. And now these charges are forced to be multiples of 4. Okay, so that was a really, really important big result. So so then we have the XY model with double vortices. Now we have this O3 model, which is one more component, but with quadrupled hedgehogs. And so now the goal is that we have to write a renormalization group flow for this. Okay, so now there's nothing we can do because nobody knows how to solve this. But there is one flow diagram that people came up with. So just like the XY model, I'll imagine that 2 parameters. One is 1 over G, and the other is the fugacity of quadrupled hedgehogs. Okay, so this flow diagram is because a very famous paper called by Senthil et al., where they discuss the idea of deconfined criticality. So I must emphasize that whereas in one dimension that flow I drew was very controlled because of RG calculations, here they're just arguments. Okay, so I can give you various arguments that it's true, but nobody really knows that this is true, and this is why we have to verify it numerically, and this is why Anders and many other people here are working on this problem, because it's very interesting and important to verify. So let me just show you what their flow was. They said that right, so basically if you take a lattice model, it has a finite fugacity of quadruple hedgehogs. Okay, there are some finite number of hedgehogs, but they said let's imagine that you can first put the hedgehog density to exactly 0 by making lambda 4 0, fugacity 0. This is very similar to the idea of Kosterlitz and Thalers, right? They take vortices away, they study the theory, then they put vortices in perturbatively. Right? So in the model, of course, it's not perturbative because there's a finite value of lambda 4. But let's imagine you can make it equal to 0. So now, the very important assumption over here, and again, in interest of time, I'm not going to tell you about this, is that even without hedgehogs, there's a phase transition in the O3 model. Okay, so this is a very, very important assumption that nobody knows if it's true. So I should say, sorry, that people are very sure that there is a phase transition. The question is whether it's continuous or first order. Okay, and actually this was first done, I want to emphasize, it was first done, people forget sometimes, by Michael Kimmel and Ganpati Murthy, my colleague in Kentucky, and then actually improved upon by Motrunich and Vishwanath. Okay, so the important idea is the existence of this fixed point. And so there's two phases over here. One is a so-called nail phase, and the other is called the photon phase. So this was really the contribution of Motrunich and Vishwanath. They showed that if you basically suppress all hedgehogs and you disorder this model, you don't get a trivial disordered phase. You get a phase which has a gapless photon excitation. Again, I can discuss, there's a way to do this and show this explicitly, but I won't discuss that today. Okay, so then the question is what happens when you put lambda 4 on? So when you put lambda 4 on, there's another very famous result in statistical mechanics that once you put hedgehogs into a theory of photons, so if you have photons and you put, the hedgehogs are basically monopoles of the photon, then they're strongly relevant and they give you a VBS phase. Okay, so this is a question. This is almost certain. So the existence of this fixed point, and this fixed point are certain. The question is the existence of this fixed point that we don't know. So suppose you assume it's true, then what Senthil et al. Conjectured is that at finite fugacity, you have some renormalization group flows which flow to the nail phase, and you have some which flow up to VBS. And now you need a separatrix between these two, and their claim is the separatrix flows back exactly to this hypothetical fixed point that we don't know exists. Okay, so this is called a dangerously irrelevant operator because lambda 4 is dangerously irrelevant because at the critical point it flows back to 0, but if you go slightly away from the critical point it's important. So it has to be included in a full theory of this system. Okay, so I was going to say a little bit more about this, but maybe I should just stop here and I'll show some slides. I want to show you some numerical data because otherwise, and I'll show you how we've tested some of these ideas. So, I think maybe Anders has already told you a lot about what I was going to say. So I'll can just maybe tell you very quickly. And these are my collaborators. Nishita is over here, and John was my ex-grad student who's now a postdoc in Lausanne, and my postdoc Matt, who's now a professor at California State. Okay, so again, this renormalization group flow shows you some way of going from the nail to VBS continuously, in which you flow into this hypothetical fixed point. So the questions we want to understand, first of all, whether this fixed point exists, and if this fixed point exists, whether this flow actually happens this way. Okay, so The breakthrough in this field numerically came from Anders, where he showed that there are these models you can find where you can actually study. So again, it's like we talked about the field theory and the lattice model, and now this is the lattice model in which you can study this in 2 dimensions on very large lattices. Okay, so you can. I'm showing you some data that I also worked on. I mean, so I'm showing you a very prejudiced view of the history. I think there's lots of contributions from many people. I mean, certainly Anders is one of the pioneers here, but I'm emphasizing my work a little bit more than it maybe should be emphasized. Anyway, so you have this nail peak over here, and you have a VBS peak in the correlation functions, and you can show that when nail comes on, VBS goes to 0. When VBS comes on, nail goes to 0. And this is some data that Anders, I don't know, is this published, Anders, or maybe not?
No, but I did show it in my talk yesterday.
Okay, so the citation is
It will be
correct.
published soon, hopefully.
So that citation is correct then?
Yeah, but it's some co-authors as well.
Yeah, those are in the brackets. So anyway, so here's a very beautiful data with huge lattices. Anders maybe has even better data now. That shows that this transition in the SU2 model looks very continuous on the largest lattices and is simultaneous between nail and VBS. Okay, so this is very interesting, and this is already, like, in some sense, some proof of this whole phenomena. But there are many other aspects of it that Anders has studied, and I'm sure he summarized it better than I can. So I'll just tell you about. So I gave you some. Okay, so I had they're there in the notes, but I wanted to tell you that the field theory that describes this critical point. So there are 2 ways to think about it. One is that you can think about it as this nail order parameter without hedgehogs, but it turns out you can also think about it in terms of a gauge theory. Okay, and so we can have an informal discussion session sometime later, and I can talk more about this with. I'm sure some students don't know stuff, so I'm happy to tell them about it. So. It's there in the notes, but I didn't get to it. So this field theory, it turns out, is very convenient because you can distort it in a way in which you can increase n. Okay, so now you could ask, what are the lattice models that this corresponds to? And actually, this was invented by Professor Kawashima in 2002, or 3, I think, when they wrote this model on SUN. So it turns out that when you take this CPN model, so there's a boson field, and you can make many components of the field theory. It connects with many components to the SUN antiferromagnet. Oh yeah, so this is the paper by Harada, Kawashima, and Troyer, where they realized that actually this model doesn't have a sign problem. And so if you combine Anders' idea with their idea, then you can study the phase transition between nail and VBS for any value of n. So that is very interesting. So again, Anders probably showed you how this, and this is what Anders was saying, and now he's also saying that these antiferromagnets, instead of doing this whole field theory, you can also think of them as some 6 vertex models in imaginary time. And so using all these ideas, we can study the phase transition for every value of n, just not n equal to 2. So the interesting thing, of course, n equal to 2 is the most interesting and experimentally important Heisenberg model. But these larger values of n are also interesting from some experiments' point of view. But as theorists, we're interested in it also because it's interesting, and we can connect with the large n limit of the field theory. Okay, so that's one limit in which this 2-dimensional problem can be solved, is in the large n limit. Okay, so these field theories, at the critical point, are described by the CPN model, and in the large n limit, we can study the CPN model. So now we can take our lattice models and study their correlation functions and ask how they reproduce 1 over n expansions in the field theory. Okay, so it's very interesting that the CPN model encodes both the nail and VBS correlation functions in very different ways. The nail order parameter is a bilinear in these boson fields. It turns out the VBS correlation function, and so now we already know, remember in 1 dimension we saw that the VBS correlation functions were related to the single vortex operators, right, in the XY model. So similarly over here, the VBS order parameter is related to the single monopole operators in the CPN model. And so if you have a field, so at large n, this model has a fixed point, and you can study the scaling dimension of this. And this is extremely technical. It was actually worked out first by Borokov, Kapustin, and Wu, who are some mathematical physicists. And actually they studied it for the case where you have Dirac fermions. But then Mitlitsky, Humley, Sentler, and Fisher even studied it. So again, this was actually originally studied by Murthy and such by some simpler methods, but these people used conformal field theory and reproduced their calculation. So based on all of this, we know the scaling dimension of the Nail order parameter and VBS order parameter at large n. And here is the data. So Anders and I studied this. So there's some issues with how you realize this in a lattice model, but there's also some work done by Anders and Chilo and Naoki Kawashima. And so if I take all the data and put it together, this red line shows the 1 over n expansion. And again, I want to emphasize this 1 over n expansion is very sophisticated. This is the leading result. So the VBS scaling dimension at large n is proportional to n, and the Nail scaling dimension at large n actually just goes to 1. Because when n goes to infinity, this goes to 0. So not only does the data actually reproduce that, but it reproduces these universal coefficients. So this coefficient of 1 over n is 32 on pi square. And this coefficient is not known analytically, but it's known to be 0.1246. In the inset you can see that you can actually reproduce these. This is 32 on pi square, this is 0.1246, and you can reproduce these numbers. Sorry, this is 2 times 0.1246. So you can reproduce these numbers at least as n gets larger. So this is pretty amazing. But then what was even more amazing is that these guys, Daya, Mizai, Pufu, and Sachdev. So Subir said the calculation was too hard for him, so he started working with some string theorists at Princeton who managed to calculate the 1 over n correction to the VBS scaling dimension. So this was done long after our numerical work. So this is our numerical work which shows the VBS scaling dimension. This line is the n equal to infinity result, and this dashed line is the 1 over n correction. Okay, and it seems to agree reasonably well. And from their paper, they note that this is among the most complex theoretical computations of critical exponents which have been compared to Monte Carlo simulations. So, I'm not showing off. I think I'm showing off on their behalf that they were actually able to do this calculation. This blue line is extremely technical computation. Yeah, I don't understand the symbols in the paper. I understand the introduction, and then after some time, they're very reputable scientists. The first time they did it, actually, they sent me a result, and it didn't agree very well, and they published it. And then 6 months later, or a year later, they wrote another paper saying that they found a sign mistake. And after they corrected, it agrees very well. So, I'm sure that. So I don't know if there's another sign mistake, but I think that these guys are very reliable. So famous people. So it's surely correct and quite amazing. Okay, but then there was another development which I think none of us over here were involved in so much initially, but I think very exciting. And this work by John Chalker and Adam Nahum and their group, where they studied something which is very similar actually to the JQ model. It's inspired by the JQ model, but it's not exactly the JQ model. It's just some slight modification of it. And all of this could be done with the JQ model, but it turns out that these people thought of the idea to take their model. And so remember I said that there's this SU2 level 1 WZW theory. And so two people, Tanaka and Hu, and Senthil and Fisher actually independently. Actually, Tanaka and Hu did first, and Senthil and Fisher came second. They clarified some of the calculations they did. Pointed out that it is possible that at this deconfined critical point, there's again an emergent symmetry between Nail and VBS. Okay, so, if this is true, this is again amazing and in some sense radical. I can try and explain to you why it's radical. The renormalization group flow that this assumes is something very unusual. Okay, and if it's true, I think it's really game-changing. And so we can talk about that later, but the important result which I'm showing you in these plots is what they studied is at the critical point, they studied the Nail and VBS order parameters, and they showed that they're connected by a rotation symmetry. Okay, so you can take the Nail order parameter and the VBS order parameter. In 2 dimensions, there are 2 VBS order parameters and 3 Nail order parameters. They form a 5-component vector, and you can test for SO5 symmetry in rotation of these 5 components. And with very, very high accuracy, they show that this symmetry is present. Okay, so this is amazing and a very, very interesting result. Okay, so I was going to talk a little bit about the easy plane thing, but maybe I'll just skip over that and just leave a few minutes for questions and show you my conclusions here. That so you know exactly like how we had in 1+1D, we're trying to establish these renormalization group flows like this one in 2+1 dimension. But you know, I really believe this is the tip of the iceberg. There's many other things, and already some things have been discovered and discussed, where the phase diagrams of these spin models, depending on the value of the spin, depending on various lattices and interactions and phases, there may be many things that we don't understand. Okay, so, but you know, here's one where we've made it. You know, it's taken a long time, but we've made a lot of progress. I'll talk about some of these tomorrow, actually, in my talk. But in this particular case, transition looks continuous on large lattices. You can connect with a large N expansion, so you can make this. So I was supposed to talk about quantum Monte Carlo field theory, and this is one case which is not. I would say it's not. I would say it'd be unfair to say it's completely understood. There's still things to understand, but at least you know, the numbers seem to line up in a way which is very convincing. There's some problem understanding scaling corrections, which I'm sure Anders mentioned, and will probably even mention more. So this is our ongoing work, but you know, there's already something very correct about this flow, but it may be that there's something that we discover. So there are two things. I mean, one is that the flow might be correct, but remember you have to interpret the flow for the lattice model, and that may not be so simple. Okay, there may be new concepts in actually doing that, and that's something that Anders is working on. We've also studied this model and in various other cases where you should get a first order transition, and it seems like you do in all the cases that we've looked at. Then there's another problem which is unresolved is, you know, if this really exists as a critical point and it has SO5 symmetry, there's some tension with the so-called conformal bootstrap. So in conformal bootstrap, remember we said that if you assume that there's conformal symmetry at the critical point, which again is an assumption, but all critical points we know have conformal symmetry, then there's some restrictions you can put on the symmetries and exponents. And so if you postulate there's SO5 symmetry, it turns out that with the numerical estimates of the scaling dimension of the most relevant operator are inconsistent with conformal bootstrap bounds. So this is again something that, you know, again something mysterious that, you know, after Nahum and all did their work, everyone was very sure that this is all going to work out. But this issue is something that, but you know, there may be, the conformal bootstrap is a very new technique in 3 dimension. It's not clear that they've ironed out everything. And so, you know, again, some very interesting things to think about.
Maybe I can make a short comment.
Yeah.
So yesterday I showed some results that don't really support SO5. It looks like the scaling dimensions for spin and diamond may, you know, be very close to each other, but not exactly the same. I can show you later.
Right.
I mean, it's still not completely conclusive, but
Yeah. So it's still amazing that they're so close to each other.
Yeah.
I mean, I think that's already
so
something
you may have
amazing.
very close to SO5 symmetry, but probably not.
Yeah. So I mean, the SO5 description is probably correct, but again, there's a question of whether certain anisotropies are relevant or irrelevant, and it could be they're just slightly relevant. I don't know. There's various things that could happen. There could be a marginal operator. I mean, in 1 dimension, we know these cases very well because we can solve it, and actually, a lot of things happen. Like even the Heisenberg chain, as you know, if you just study it, it has this emergent symmetry, but if you just studied it, you may have concluded it doesn't exist because of this marginal operator that messes things up. So you know, that and much worse things could happen in 2 dimensions. So you know, there's lots to think about and worry about, and I mean, but the beautiful thing is now we have models where we can maybe answer these questions. Okay, I didn't talk about easy plane criticality, but I mean, you can take XY models and disorder them, and there's interesting questions about the phase transition there, but maybe some other time. Okay, thank you.
I have one question at the last piece of statement. According to Kenji's calculation, for SU2 case, okay, at least approximately SO5 seems to exist, but in the case of SU3 or SU4 model, I mean, the values of eta are completely different. So I mean, is there any reason to expect this behavior? I mean, only why SO5 kind of symmetry exists only for SU2 case?
Yeah, that's a very good question. Yeah, I mean, I've thought about this on one. I mean, so it's clear that when you make n larger, even in this 1/n expansion, we know that the Nail and BBS scaling dimensions are very different. So there's no symmetry that can rotate them. N equal to 2 seems to be special, that it has this symmetry. So, but again, to formulate it in a field theoretic point of view, is the question is that you have some order parameter, right? And so, of course, right. So the question now is, if you take this vector phi, so you have some, people write some very symmetric theory like this. So in one dimension where this works out, it turns out you can prove in one dimension that any, so technically you're allowed many, so in fact I think I wrote it over here, the equation I want to write down. Is there many of these so-called anisotropy operators? Because the microscopic model doesn't have O5 symmetry, it has much lower symmetry. So you have to put in the anisotropy operators that bring it down to the microscopic model. Then you have to prove that all of them are relevant except for one, which is the tuning parameter of the critical point. So that is an assumption. And actually, I don't know if there's a good reason to assume that's true. I think that's just, these guys just assumed it. Because they said, okay, if it's true, then it's very beautiful. It's sort of like, so in one dimension, you can show that there are no operators which are relevant. That's why you can reach this SU2 level 1 without tuning any parameter. You just put the Heisenberg model, you simulate it, you don't have to tune anything, and it goes into this critical phase. Then they assume that in 2 plus 1 dimension, there must be one relevant parameter. So now it could be that, when you study SUN, you have more of these order parameters, but there may be more and more anisotropy order parameters allowed, and so you can't reach this highly symmetric point by tuning just one parameter. You may have to tune more parameters to reach that point. So it may be the theory of a multi-critical point. I'm not sure which one. But that's just a thought. I don't know. So it's only believed to be true for SU2, but that's a very good point. And so the question is there some hidden symmetries for larger n? I think we don't know the answer.
I see.
Oh, so can I ask a following question from Professor Kaul? So is there any fundamental difference between those SU2 model and SUN? N is larger than 2? Or it's depends on the N is odd number or even number? Is there any fundamental difference? Or the critical theory they proposed is NCCP and -1. So for their theory, is that any special thing about n equals 2 or n is even number or odd number?
So at the microscopic level, there's nothing special about n equals 2, at least as far as I know. Again, the fact that this symmetry exists is an emergent property, or that it may exist is if it exists at all, it's an emergent property. So it's well beyond how the microscopic model is designed. Like you couldn't tell by looking at the microscopic model. But that's always true about emergent symmetry. Just by taking the Ising model, you can't tell. There's no way you could have guessed that the critical point has an emergent symmetry. So similarly here, the critical point and its emergent symmetry, as far as we know, is not related, or at least as far as I know, is not related to any microscopic property of the model. It's something that so it's because, again, the question is how many relevant and irrelevant operators there are. If they're just the right number, then you could get the emergent symmetry.
Yeah, but I think sometimes it's not just about the emergent symmetry. It's because maybe for SU3 case, it is for SU2 and SU4, it's highly likely to be continuous. But SU3, it seems that it could be a first order. So I don't know if 3 is special or.
Yeah, it's possible. I mean, there may be something we don't know. In fact, I'm sure there are many things we don't know about, but that may be one of them. Yeah, I mean, I think as far as the CPN model is concerned, it doesn't really distinguish between 2 and 3. They all seem about the same.
But this SO5 theory that they have written down as an alternative field theory, that can only be done for SU2, right? But they haven't proposed any generalization for the higher end.
I think there may be some generalization, but it may be hard to argue that it has only one level operator.
Right.
And in fact,
But I don't think they have even written down
Yeah,
such theories.
yeah.
But maybe one can speculate that it's possible.
yeah. I think it has.
But I think they emphasize in the papers that this is really a special theory for the SU2 space.
I agree. So there may be other special things about 3 that we don't know.
Right.
In the CP1 thing, 2 and 3 don't look very different. But you're right. In this thing, this is very special to 2. So there maybe there's lots of. So if you didn't know this, you might have said 2 is just like everything else. But apparently 2 is very special. So it's possible that there's other special things that we haven't discovered yet.
That VBS fixed point you drew
Yeah.
for the RC flow, that's for 2D square lattice,
Yeah.
right? So in principle, you can have columnar VBS or Leggett VBS. They should correspond to different fixed points. Is that correct?
Yeah, so I think it's sort of like in 1D, there's that lambda, and there's a cosine potential, and I think it depends on the sign of that lambda. So, in principle, there's, you could go here, you could go somewhere else, depending on the sign of.
So even for 1D, you can have different types of VBS, you mean?
In 1D, I think you can have just one VBS.
Yeah.
But this lambda 2 relates the Ising nail phase and the VBS in 1D.
Right.
The lambda 2 of the vortex.
But in this case, you will have 2 VBS fixed points.
Yeah, I mean, there's other VBSs as well, apart from this. Like there's a staggered VBS.
Oh,
There's many different VBSs. But I think it's the columnar and the plaquette ones which could be consistent with the deconfined criticality. People have argued that in fact, Anders and Arnab Sen studied some other ones and found first order transitions.
But so you could have, I guess, to clarify what June said, you could draw some diagram where you have 2 VBS fixed points and you could have flows even going close to one and then it bends over and goes to the other one.
Yeah,
in principle.
I think so, yeah. I think you could have more than one VBS. Apart from the for the full square lattice symmetry, I don't know if anyone has a model yet which has this plaquette VBS. But
June has one.
so maybe I don't know about it.
June will give a talk about that on one of the Monday.
29?
Cool.
Anything else? Okay, thank you again.